talk about this pattern of finding distributed systems. I will have to take a moment to understand what's going on. This is the type of distributed system writing that I see very often, which is absolutely correct, it's self-documenting, and utterly useless. So, usually when we start talking about distributed systems, we have, lot of stuff. Okay, much better. So usually when you talk about distributed systems, we have to make a lot of decisions. I've been working with distributed systems for the past 8-10 years. I've been working on RavenDB specifically to make a really awesome database for the better part of 6 years now. Just to give you some idea, one of the things that we really wanted to do with RavenDB was actually get something that you could get working and you wouldn't want to go and have a really, really big glass of whiskey or vodka just to forget that you had to do stuff to it. So, by a show of hands, how many of you have used RavenDB? Awesome. Great. So, RavenDB is a NoSQL database. It has drivers for a lot of languages, .NET, JVM, etc. High performance, scalable, and distributed. Other things that make it more interesting is that this is safe by default and it's ACID. So that pretty much means that you get to use it on high-end systems and you don't have to worry that you put data into it and then it just goes away. So RavenDB is actually used quite a lot internally inside in Service Bus. Unless you have taken specific steps to prevent that, whenever you deploy in Service Bus, there is a RavenDB component internally that handles basically all of that. A lot of that comes from the part that we don't want to make it hard to work with in Service Bus. And RavenDB as a component internally make it very easy to use because you can just throw data into RavenDB. It will manage that, work with that. It's very easy to work with. To those of you who haven't seen RavenDB, this is RavenDB 3.0. It's an upcoming version. And this is more or less what it looks like using the Northwind database. To those of you who are feeling very passionate about that, this is not a Silverlight application, this is an HTML5 application. Yes. By the way, I feel very, very strange standing here telling you that the major part of our major release is going to be a different UI. I'm a database guy, I build databases, and people keep asking me for different UIs. So anyway, this is RavenDB. This is how you store data inside RavenDB. As you can see, this is JSON, and that's pretty much it. The interesting thing about RavenDB is that this is not just an issue of, oh, I have this amazing text box into which I can throw JSON and I have it color-coded. One of the things that we can do with that is external ID. And now we found this guy. Okay? Anyone here is amazed by this feature that we are able to query by a property? Anyone here thinks that this is the feature that we need to talk about? No, right? I mean, it's fairly obvious what's going on. Anyone here ever had a system go down in production because of a table scan? I don't believe you. Yeah. Okay? How many of you ever had a system that went like that? We deploy to production, everyone is happy, everything is going well, and suddenly, over time, we have more data, more users, and things just become slower and slower. And then they stop. Unfortunately, they always stop when I'm on vacation or asleep. So, one of the things that we wanted to do with RavenDB is to ensure that we will stop those kind of issues. Now, why do we have this issue? Why do we have a system that becomes slow over time? Anyone? Yes. Sorry? Memory leaks. Hopefully we don't have it in RavenDB, but that's not what I'm talking about. Why do we have systems that become slow over time? Sorry? More and more data. What's the problem with having more and more data? Indexing, or rather more to the point, the lack of indexing. If I wanted to do something like that in a relational database, select star from company where external ID equal X, what would the database do? Well, it would start reading all of the rows in the table one at a time, a very simple and elegant ON solution. Over time, we have more data. What happened to the simple and elegant ON solution? It's still simple, but it's not so elegant anymore. What I want to show you now is the query start for this query. And you can see this guy. So what's going on in here? We actually did use an index here. And the index that we used was auto/company/by external ID. Now, let me do another query. Name Wolski Zadjazd. Anyone here from Poland? I apologize. I assume that this is... Oh, I could just copy that. Oh yeah, 2 spaces. And now I get this guy. If I'm looking at this, you can see that I have this index, auto/company/by external ID and name. What is this? This is an index. And it's going to index the name and external ID properties of companies. Who defined this guy? Raven did. The hint is that this is an auto index. So remember, one of the things that we said about RavenDB, it was that it was safe by default. This is a very simple example of how it is safe by default. When you make a query in RavenDB, we aren't going to go with the ON solution. ON solutions are wonderful for demos because they make it very easy to do things rapidly and without really thinking about them. And they are horrible for production because they're effectively poison, and they are slow poison. So your system is working, and over time it stops working. So the question now becomes, how do you use RavenDB in your own systems? Everyone here is presumably at least already using in Service Bus. So you're using in Service Bus, and Service Bus use RavenDB, so you already have some benefit of that. But what would you use RavenDB for inside your own applications? Sorry. One of the major things that we built RavenDB for was for the notion of domain-driven design. The notion of, instead of working with rows and columns, and if I have this order document, if I have this order, so I need to split it to 7 different tables, now we're working as cohesive documents. Let's see what a document looks like in RavenDB. And specifically, I want to look at an order. Better. Okay, so this is an order document. What can you tell me about this order document? Sorry? Okay, what else? It's Matt? Okay, so Matt uses the term denormalized. I don't like the term denormalized because that implies a specific way of thinking that is usually relevant only for relational databases. But all of the data relevant for the order is located in a single place. Now, notice that we have data that is relevant for the order, but not necessarily related to it. So, for example, this order is shipped via shipper 2. I don't care about anything about that, whether it's UPS or FedEx or anything else. So it's not included as a part of this cohesive document. But I can look at this document and see what's going on. And I don't need to branch out to separate tables or additional documents just to see what's going on. If I was trying to model this in a relational database, how many tables would I need? A minimum of 2. In the Northwind database, to load a single order, I need to touch 7 to 8 tables. And that's really a 10-plus-year-old sample database. So that's about as simple as you can get. So entities and aggregates. What is an aggregate? An aggregate is the order. Any change happening to the order happen to the whole order. I can't add an order line and change the address concurrently, because there are business rules that says that no, this item cannot be shipped to this location. If I would allow concurrent changes on the order, that would mean that I'm opening myself up to race condition in my business logic. Aggregate also means that I have all of the information related to a specific business concern in a single place. Another issue is the notion of complex object graphs. As you can see here, we actually have some simple properties. Here you have the ship-to object. We have a collection that has complex objects. This is a much more natural way to model data than let's throw things into as many tables as possible and hope that we buy a big enough server. Finally, we have the notion of what sort of operations do I want to make. And this is where we actually get into the interesting stuff about how do we make use of RavenDB in a distributed system. So I actually took this from the Oracle documentation. Anyone here wants to tell me how many ways this is going to fail? Here we have a lot of distributed systems, and here we have the shared databases. How many single points of failure do you see here? That's a problem. That's a problem because one of the cardinal rules of building robust distributed systems is that I trust myself, and even that not so much, and I'm most certainly not going to trust anyone else. Anyone here ever had to work using departmental databases or works organization-wide databases? I'm talking about those databases that have 300 to 400 tables at the minimum. I'm talking about those databases that have 60 to 200 applications sitting on top of those databases. I'm talking about those databases that goes down apparently at random for a relatively long period of time. And then people come to you and say, why is your application not working? And it's the DBA's fault isn't really a good answer to that. So in a distributed system, I trust myself. I do whatever I need to do internally. And any communication that I need to do with the outside world is going to be done through very specific channels. Hopefully through one-way messaging, so I can send it out there and let a queue worry about how it's going to get to the other side. And if the other side is an app, or it's going, or it's just going through a GC cycle, or maybe, you know, someone trip over the power cord, or any of those things, I don't really care. I once built a distributed system where one of the components in the system was named Jane. Jane wasn't the name of a computer. It was literally the name of a woman who was sitting at an office, and her job was to evaluate stuff. And she would basically go over a list of stuff that she got by email, and she would click on a link. Yes, this is approved. No, this is denied. As you can imagine, the latency of Jane was pretty high. That was especially true when she took her weekly vacation, in which case processing a message would take about 3 weeks. But from every other perspective in the system, Jane was a component. We actually have a Jane bridge that walked between them. This is something that I feel very, very passionate about, okay? Sharing data. This is coming back to the same idea here. Let's take my wonderfully beautiful, amazing distributed system that is composed of, 16 different business components and 19 different endpoints, and everything is beautiful, and let's put them all on the same database. Because that's going to work very well. Especially when you have a burst traffic in one endpoint that's going to have a rolling effect over on the entire system. Now, the problem here is that Matt said before, denormalization. How many of you think about denormalization as a dirty word? How many of you have heard over and over that you should normalize that? This is data duplication. If you go down that route, there is a big horny devil that is going to take a pitchfork and stick it, I don't know where, but it's going to be unpleasant. Okay. And that leads us to situations like that, where, okay, I have a user, I have a customer. In how many places am I going to need to look at a customer? Let me talk for an example about my own business. And we have the notion of a customer. We have the notion of a customer who buys software. We have the notion of a customer who buys support. We have the notion of customer who actually start a support incident. It's not the same customer. When I'm looking at the help desk function, the kind of data that I need is utterly distinct from any data that I need for payment processing, from the kind I need to order fulfillment, for the kind of data that I need to, cross-selling purposes. It's the same customer. Again, let's talk about Jane. Jane wants to buy RavenDB. Jane wants to buy a RavenDB hat. Okay? So, she comes to us and says, okay, my name is Jane. This is my credit card number. This is my address. Send me a hat. Okay? I will send you a hat. Now, at the same time, there is a different system that's going to say, okay, we have a new order for Jane. Let's look up its order, her order history, and see what we know about her, and see if we can offer her additional stuff. Instead of just getting a hat, why don't you get this nice bag? It's very chic. At the same time, Jane calls us and says, you know what, I didn't get my hat. Where is my hat? So that goes to the help desk function. Same person, lot of different roles inside the same company. Lot of different data that I need to handle. When we're talking about slightly bigger customers, then we have Jane who is the purchasing manager. We have Joe, who is the developer on the trenches that says, look, I need to do X, Y, and Z. How do I do that? And internally inside my company, I have Sabrina, who handles the order. I have Michael, who is actually handling support. You have all of these different roles. By the way, I'm going to take a pause for a second. One thing that I found to be very, very helpful in modeling distributed systems is to talk about them in terms of people. So Sabrina is my order fulfillment process. Michael is my help desk function. Both of them, by the way, are real people, and that's their jobs. But when I start talking about the software component that they need to do their jobs, I'm not saying we have the order fulfillment component. I'm going to say that Sabrina is going to do X, where Sabrina is a business component that the actual Sabrina person is going to be using. It helps a lot because that means that unless I have Siamese twins working for me, I don't have people sharing the same brain. Because at that point, what I'm going to need to do is to share the data, but when I'm sharing the data, I'm not sharing the same copy of the data. I'm not telling you, okay, all of our customers are located in this location. Instead, I'm going to say, okay, Sabrina got a new order. She will let Michael know that that ID so-and-so has a support contract for 24/7 enterprise support. And Michael is going to make a note of that in his notebook. And when we get a support call, he's going to check his notebook. He's not going to try to talk to Sabrina, hi, is this order relevant? That's why I said that I really like talking about distributed system in terms of people, because it makes it much easier to talk about the interaction, and because hopefully you don't get these kind of people. So how do we actually model a distributed system? Specifically, how do we model that with regards to the data distribution? If we talk about the customer, so the customer have an order, they purchase production support. That data is in sales. Sales generate a message that says, create support contract, and the help desk create a support contract, maybe send an email, this is how you open how you open a support incident, and this is how it works. When Michael gets a support call, he checks his own data. There are a couple of interesting implications of that. One is that Michael and Sabrina don't have to agree on what the customer looks like. They don't have to coordinate when they make changes. All of that was a preface to talking about how we can actually do that with RavenDB. So now we are looking at a single endpoint inside your system, and you can see that we have the queue, incoming, outgoing messages, we have the actual message handlers, Saga handlers, and whatever, and we have our own RavenDB that does things, that store data. Right now, by the way, I'm talking about the RavenDB instance for your own explicit use. I'm not talking about the RavenDB instance that N-Service Bus used to manage its own data. Okay, so this is what it looks like. The sales DB has all of the relevant data for sales, and then we have relevant data from this point from another location. There are several ways of actually managing that. One way of doing that would be to say, okay, I'm going to have explicit message passing between my components. Whenever I have a new user, Then I'm going to notify all of the other components that can record that data. Another option would be to actually have a local copy of the remote database. For the most part, what I would recommend is to go with the message passing style. The message passing style means that you have to do more work. The problem with doing all of this more work is that it generally doesn't pay up front. So you have a new user coming in, and you need to record that in the manufacturing database. So you have some code that basically says, okay, let's take the message from the bus, let's copy these X properties that I actually care about, and let's save it to our database. And that's stupidly silly code. And you have to write a lot of that in any big system. Take some properties from here, save them into the database, move on. Now, the reason this is stupid is that you effectively create a clone of the same data, sometimes even of the same shape that exists in another component. And the reason this is important is that 6 months down the line, a year and a half down the line, when you need to change the sales in any meaningful way, you can do that. You can change just the sale portion of the system very easily, because the only communication between the two pieces are using messages. I know that you probably know all of that, but I want to get into how we are actually doing that. So let's talk about how we actually distribute the data. I mentioned that one of the ways to actually have a local copy of the database, I want to show you how this is done. I'm going to start from scratch. Define a new database. Then I'm going to define new user. Now, seriously? No. Too small. Settings, replication. And that looks good. Notice that we are now in the slave database. We have this guy. Now, I'm going to go here and create a new user. And sorry? Yeah. Okay, so in a bit you can see, the rest not so much. Anyway, so as you can see, what we have here is actually seamless replication between these two guys. And that works very nicely. Another option that we have is to actually have something called SQL replication. SQL replication gives me the options of writing a script that would take the data from my database and replicate that into a SQL Server for reporting purposes. It can be SQL Server, Oracle, Postgre, basically anything. When we're talking about that kind of data sharing, that's something that I'm actually much more comfortable with, because I don't have this single process that just dumbly copy data from one end to the other. The RavenDB replication is very nice for high availability, for throughput. It's not so good for actually managing data distribution for one reason. Because you now have coupling between the different components, if only at the schema level. It's better than having a single shared database. Now you have your own database node that you can access, and you know that, well, if this database node is down, this endpoint is down anyway. And the replication that we are talking about is replication that happen async and behind the scenes, so that's good for our purposes. With SQL replication, I get to shape the data out. The other side of SQL replication is any sort of ETL processes. You're probably familiar with them, with that job that runs at midnight. No one knows what it does, and it takes 3 hours, and stuff happens with that. And somehow, magically, stuff moves from one database to other database, gets churned up a bit. Sometimes there are bugs. We hope no one notices. Okay. These kind of details are also a way of sharing the data. I intentionally describe it as a very bad process, but for a lot of the stuff, this is actually quite useful. Because you have a well-defined process, or you have a process, well-defined is something else, that take the data from one end of the system and push that to another end of the system. And now you can tune that process based on, okay, I need it to run every 15 minutes, I need to run it every 24 hours, or stuff like that. A lot of the time, we use that kind of system to run on reporting systems, to run the nightly reports, or stuff like that. But there isn't any reason why we can't use the exact same process to move data around between our systems. It's not messaging, but it is a process that we can live with. And even if you know you have a failure down somewhere in the middle, it's repeatable in the sense that, okay, we will restart this database, we'll make sure that the router works, and renew the process. Dedicated messages are, as I said, much better in terms of architectural clarity. The problem with them is that they're also much worse in terms of the number of times that they have to write message.name equal entity.name on both ends. One to publish that to the world, one to consume that. And if I have a system that is composed of many components, that I have to handle that in each and every one of them. That's kind of sucks. The good thing about it is that we have a very clear data ownership. The bad thing about it is the duplication. What's the problem with duplication? Again, why is denormalization a tool of Satan? Keeping it up to date. So the problem, the moment that we have shared data, the moment that we have multiple copies of this data, how do we keep it up to date? And at this point, we may realize something quite interesting. A lot of the time, not only don't we have to keep it up to date, it would be very wrong of us to try. Let's consider the following case. We have the HR component, and the HR component publish a message, pay John $10 for his work this month. And the payment processing component is going to say, okay, I'm going to cut John a check, and that would be it. 2 weeks later, we're going to change John's address. What's going to happen to the check that was already sent? Do we have a way of magically calling FedEx and telling them, you know that package? Move it from this location to this location. What do you mean you already delivered that? Break in, take it apart, and then move it to that place. It's important that we don't have any duplication. The truth is that for a lot of the stuff, there is historical context that really, really matters. If I cut a check for John at 123 Widow Drive, then I really want to know that this is where it was sent. It's very, I've seen multiple systems, especially I worked on payroll system for a while, and I've seen multiple cases where trying to do the right things in terms of normalization meant that you got a raise mid-year, and then we have to send a report for the IRS that this is how much money you made this year, and oh yeah, we didn't count all of the months before you got that raise. So now you owe a lot more money to the IRS. That one at least we caught in testing. So when we talk about duplication, we really need to talk about what kind of data are we talking about. Is it data that is actually relevant now, the current value? Or is it data that is relevant when that thing actually happened? I don't care what your name is, I only care what your name was when I issued that check. Sorry? Okay, yeah, that's fine. Did you hear what I take? Why? Blah, 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 blah. Did you hear what I said about the different data types that we duplicate? One of them that is immediately consistent, one of them is a point-in-time reference. Okay. Another way of talking about managing data in a distributed system is via CQRS. And this is where it starts to get interesting. This is where I see a lot of people start to get this light in their eye. It's buzzwordy, it's nice. And it's basically, instead of just throwing messages on the bus and the other side, we're going to just copy them into our own data. We're going to start having event streams. And instead of having to deal with the data as it is, so okay, we have user coming in, so we need to have the new user register message handler, which copy the name and the email and save it to my database. Instead, I just have all of those events, and then I work with them outside. Let's see how this works. With RavenDB, we store events as messages, and then we can process them as a MapReduce operation. MapReduce might sound scary, but let's see how it works. We have the order process events, and in the sales endpoint, we need to be aware of, okay, how much money did we make on this customer? When was the last sale by this customer? Can we see a graph of his sales? That kind of things. Now, if I would try to do something like that directly out of the fulfillment business component data, that would be kind of hard. If I'm trying to do that on top of the events, I can do it like this. Notice that we have two sections here. One of them is the map, in which we go over all of the order process events and get the data that we need from it. And then we have the reduce, in which you say, okay, by customer, product, and year, let's get a count. The nice thing about this thing is that this is always running. So I have my events that I throw into RavenDB, and instead of having to write all of those message handlers to get the data that I need, I can do it the other way around. I can say, okay, let's define the aggregation that give me the data that I need. If I need to know what is the valid support contract for a customer, I can get them from the order process event. And this is where the business logic for the distribution, for taking the data and making it do the kind of thing that I need, comes into play. Okay, so what kind of answers do we get from MapReduce? One interesting thing is that the answers are immediate. MapReduce in RavenDB runs in the background. It pre-computes all of the results. And when you ask, okay, show me how many products did we sell in this year, it's insanely cheap for me to do so. Because instead of having to go over the entire data set and then aggregate that, I have already aggregated everything, and I'm just going to check the pre-computed results. Instead of having an ON square, I have an efficiency of O log n. Okay, this is fun. I'm going to crash right now. Big enough? So this is some RavenDB code. This is the document store going to the user's master database. And this is us reading some data from RavenDB. And you can see that we got this lovely result. No one should be surprised by this. Now remember that what I did before, I defined replication between those two guys. I'm going to disable this database. That means that I can't go into this. Whenever I'm going to get into that, I'm going to get an error. Could not open this database. Now I'm going to run this again. And I'm actually getting the same result as before. Let's try doing something slightly more interesting. How does this work? Remember when I told you that RavenDB was designed to be a really easy database to work with? One of the ways that it was designed to be easy to work with was how do we handle distributed systems? In a distributed system, we have to think about the fallacies. And we have to think about failure always happening. So we have defined replication between those two databases. And one of those databases was down. That's okay, I can live with that. I'm just going to use the other database. By the way, notice that at no point did we actually have to define that. We didn't have to talk about topologies, we didn't have to talk about anything at all. Now I'm going to go here and enable this database. And now I'm going to say, okay, whenever we have a failure, I want you to read and write from the secondary. So let's look at that. Yeah, it would help if I close this. Okay, now I'm going to look at this guy. He has an age of 1. I'm going to run it a few times. Now I have an age of 6. If I'm going to look at the second database, the slave database, age of 6. Great. Now I'm again going to disable this guy. again. Oh, sorry. I'm going to do that again, and as you can see, this guy just works. And if I'm looking at this guy, we have age of 10. Now I'm going to take this back up. This is still 6. This is because we defined a master-slave association. I'm going to go the other way around. Now I'm going to the master database. I have this guy. So this is what we talk about when we talk about high availability. Transparent failover, the ability to, you have a database that is crashing, no worries, we'll switch over to the second node. When that one is up, we will fill in all of the details, everyone is happy. We also have the ability to do load balancing. Load balancing here basically means that, hey, I have two databases. Usually they are different nodes, not on the same server. So why am I having one of them do all of the work and I want just going like this? So I can define that I would read from all servers, and RavenDB would transparently shift all of the work in a round-robin basis between all of the nodes that I have. This is interesting. How many of you are using the database? Anyone? Just a few. Okay. So RavenDB is a distributed replicated file system that is meant for handling two interesting scenarios. One of them is large files, hundreds of megabytes, multiple gigabytes, that kind of things. The other one is many files, hundreds of thousands of files, that kind of things. So this is part of RavenDB 3.0. Here you see some images that I have in the system. How does this relate to RavenDB? Well, one of the ways that this relates is you can use RavenDB as a database. You have the code over here that does that. The good thing about it is that now you have the same benefits of replication, transparent failover, all of that sort of things. RavenFS also has metadata that allows you to do a lot of interesting things, such as, okay, I want to see all of the data related to this customer, or about this message, that kind of things. More interesting, and usually better, is when you actually use RavenDB directly, RavenFS directly. Think about a scenario where you have a user that uploads videos into your system, and you have a set of components that needs to do some sort of transformations on this video. Maybe thumbnail generation, maybe it's, quality changes, that sort of things. In that cases, we can take advantage on the replicated nature. So the web component uploads the file directly to RavenFS. RavenFS then transparently in an async process send that to the second node. Your transformation component is getting notified from RavenFS that something happened, a new file arrived, transform that, write any changes to its own copy of RavenFS, and this is distributed to the entire cluster. Here is a very small trick, it's very nice. This is what happened with Service Insight. When you start throwing all of the data inside RavenDB, you can see how this looks here, and you can track that. But you can also start doing more interesting things directly. Think about how much state you have in your Saga, and you aren't limited to just, okay, let's look at one at a time. You can have replicated data. You can have map-reduced information. So I want to see how many of my sagas are in the open state. I want to see, I want to get the data out to a reporting service. Maybe I want to do an OLAP cube. A lot of that can be done very easily. I don't have enough time to actually demonstrate that, but that's it.